Hi everyone, welcome back to the Redfox Security YouTube channel, and I am Siddharth, a security consultant at Redfox Security. I'll be your host for today's Wednesday live session, and today we are going to be talking about native API. Now, the reason I picked this topic up is because a lot of malware development starts off with Win32 API because that is complicated enough for you to start with, right? However, the thing with Win32 API is that it takes, it makes its place in the import address table of whatever binary you compile. Hence, it's pretty easy to detect, and programs like PE Studio are very easily able to identify what kind of functions you're going to be using in that binary. So just static analysis sometimes gives the indication what a binary would try to do, right? So let's dive right into it and see how we can use native API to not get booted off or not get our malware purged just by during static analysis. So here we have some basic code for a shellcode injection. Now I'm going to start off with basic remote process injection, and this is a Win32 API code. So I'll explain it really quickly. Just a few library imports, some definitions which are going to help us later. Some more variables have been initialized as null. Here is our handy shellcode generated from MSF Venom. This shellcode basically parses the process environment block and locates the functions it needs to start calculator, right? So this shellcode this is essentially a position independent code which will start up calculator, calc.exe. Now here we get to the main where we are taking in command line arguments, one to be precise, which is going to be the PID, and we're going to convert that into an integer and store it in this variable called PID. Next, we use the open process Win32 API to open a handle to whatever remote process we want to, right? So first we spot that process, get its PID, and then hand it to this particular binary. Next, we do some error handling just to make sure that the handle that we have received is not null, because if it is null, then there's no point in going further. After the error handling, we create a R buffer or a remote buffer in this process to which we have obtained the handle to, and we get rights to reserve and commit memory to it. Moreover, the permissions of this memory space is RWX, or read write execute. Now this in itself is an indicator that it might have some kind of a shellcode, but this is enough for our demonstration, right? We can modify it while developing much more robust malware, but it's enough for our demonstration right now. Moreover, there is more error handling after it, just to ensure we have successfully allocated space in the memory or not. Also, do note that the size of the memory that we're allocating is equal to whatever the size of the shellcode is. Further, we write the contents of shellcode to this remote buffer that we have created, and again do some error handling just to make sure that we are actually succeeding in doing all of these things. Finally, we create a new thread in that remote process and ask it to start its execution from our buffer, right? And since this position independent code is present in our buffer, therefore this thread will execute calc.exe successfully. Finally, we do some cleanup here and there, right? And then we exit the process. So let's actually see this run. Right. So first, let's see if this even works or not. So the PID of this particular PowerShell window is 14276. So I am going to execute shellcode injection.exe, the source code to which I was just displaying right now, and hand it the PID for this particular PowerShell process. And as we can see, calculator.exe has suddenly spawned from somewhere. And moreover, since a new thread was created in this process and it's not really managed that well, this PowerShell window dies as soon as I try to do anything else. However, calculator.exe is working perfectly, right? So this is calculator.exe is just a placeholder for any of our malicious shellcode. Maybe it could be the shellcode to a C2 beacon, right? Something like that. It's just a placeholder for it. So now let's have PE Studio take a look at shellcode injection.exe, right? And while that happens, let's also open up shellcode injection.exe using a handy dandy debugger called x64 debug. Right. Now I have placed breakpoints in the main, right? So here is where the main starts from, right? So this assembly is where our whole execution of the code that we've written is actually starting from. The code before this is just preparing the environment for our main program to execute, right? So here we have a lot of instructions in the beginning, right? And let's pull this over here, right? And we can give it a new PowerShell window. And change the command line for the same. So this time the PID is 5132. Okay. So as we can see, this top right black command prompt is essentially the program running, right? So as I go through each instruction over here, you might be able to see changes being made here and there. And a lot of this code that you can see in assembly, you might be able to understand what it means based on the English you can see right next to it, right over here. For example, the next call that's here, right? You can see the English right next to it, that the RCX is going to get this particular sentence, right? So this is most likely a print statement. And as soon as that is called, we see that PID, okay, this is the wrong PID, I did not restart it. We can see that the print statement has been called. And as you scroll down, you see that there is open process right here. And then the error handling part of our program is somewhere here with get last error. And scrolling further down, we have virtual alloc x, we have write process memory, we have create remote thread. We essentially have every Win32 API right here, and we can tell that this is exactly what the process or the binary is going to do or try to do, right? And it's not just during runtime. PE Studio, if we open up PE Studio and go to the indicator section, what we can see is that imports is flagging a lot of things, and that's causing the binary to be classified as malicious or closer to malicious. And once we take a look at the flags that that are being raised, in the import section, we see that open process, write process memory, virtual query, virtual protect, virtual allocx, all of these are present here, along with create remote thread X, but it has not been flagged. However, we can still see it, right? So the agenda of using native API is for these processes to not show up in the import address table, right? For them to not show up in the imports. Now we can, one thing we can do to actually achieve this is to, get these processes to get loaded into our binaries during runtime, right, dynamically. However, we can go one step further and not use Win32 API at all and abstract down to native API. So we are not actually calling a function from kernel32.dll, right? If we actually see what is happening when open process is being called over here, we see that this right here, rax is going to call open process. If we hover over it, we see that it's redirecting us to another memory location. If we go to symbols over here, this green symbol right here is essentially indicating what memory space or what memory space we are in of which module, right? So currently we are in the memory space uh, of shellcode injection.exe, right? Over here, yep. And as soon as I step into this call, I am suddenly at a memory space where there are no instructions above or below it. And in the symbols, I can see that this memory space belongs to kernel32.dll. Moreover, if I scroll up and down, I can find more Win32 API calls, which are just jump statements over here. These are not handled calls over here, right? These are just basic jump statements. So let's step into this again. And if we go to symbols, we can see that now we are at kernel base.dll. That is the memory space we are in, right? We are inside the module kernel base.dll, where we can see that there is some management code over here, right? This is probably restructuring some kind of data that we have pushed to different registers. And then it calls yet another function, which is the NT-open process. Now when we step into this NT-open process, then suddenly we are in this memory space of ntdll.dll. That is the module which we are in. And this is the very short piece of code that there is. Now if I go over this and let the syscall run, now we're going to be back in kernel base.dll. So the system call is being carried out from ntdll.dll, and we are essentially just using kernel32.dll and kernel base.dll as ways to reach the ntdll.dll. So in case somebody is hooking the Win32 API, right, then we can get by it by directly interacting with the native API, right? This is one way. This is one way which in which you can develop some malware to evade Win32 API hooks. To actually perform this, we need to understand how we can call this NT-open process. However, these are not really documented by Microsoft. For example, if we go onto the web and we try to search for open process, so we have this whole documentation by Microsoft itself, which tells us how we can interact with this function and how we can use it to perform different, um, any desired outcome that we need. We can use this to do it, and the exact parameters that we need, the exact data structure, the exact size of those data structures, everything is in here, along with what return values it is and additional remarks. We also have examples for the same. It's essentially a treasure trove for any kind of development involving Windows. However, where we want to have an interaction with the NTAPI, right? Now, a lot of reverse engineers have worked on this to create something called the NT-doc, and we can use it to interact with the native API directly. This has been done by reverse engineering the calls and trying to figure out what the structure of the parameters is like, right? So, for example, what I'm going to do in this case is, first let's close the debugger, right? And I have created a copy of shellcode injection.c in transition.c. So right now, this is the exact same code. Right? I'll go over this slowly so you can see that it's just the same thing, the exact same thing. Open process, R buffer, um, yeah, virtual alloc, create the R buffer, then write the shellcode into it, then create remote thread X, and then clean up, right? So it's the exact same thing. Now, as a demonstration, what I'm going to do is replace one of these APIs and try to see if that makes any difference in how PE Studio actually looks at this piece of malware, right? Or rather, this piece of random software. So I'm going to target open process, and the idea is to replace this. So I'm commenting out open process, and I'll use the reverse engineered native API to actually carry out this exact same thing without anybody knowing that I am trying to run open process. So as we saw with the debugger, uh, the open process is essentially a wrapper around the native API called NT-open process. So here is this website which is NT-doc, right? And it has all the documentation required to interact directly with the native API. So this is how the native API is ideally supposed to be called or defined. So what we can do is we can pick this up and define a floating function pointer which we can later use after tracking down where this function exactly is. Right? So here we have defined a function pointer for NT-open process, and this is just a structure. This is essentially telling us that this is how this is the exact parameters that are required to call a function, right? And which has yet not been defined in memory. So we are not creating a function over here, we are creating a function pointer. Now, as you can see by these squiggly lines over here, there are things that are undefined in the project right now, in the code right now. So we can further use NT-doc to take a look at these structures which have not yet been defined. So one of them is client ID. We can very easily and simply just copy that and put it here, right? And as soon as we put it there, the squiggly line is gone. Now, one more variable or type is not present here, which is the object attributes. Now here I'll introduce you to the Virgilius project, which is essentially it's going to help you understand, or rather keep track of how these different structures change over time with different versions of Windows. So currently I'm using x64, Windows 10, and the Vibranium R5 update. And right now I need the object attributes. So this structure is what I go to. Now you can see a timeline above in which you can take a look at different changes that the structure has went through with different updates. I don't think this version has gone through a lot of changes over the years. Either way, we'll just take this and put this over here, right? And as soon as we do that, the squiggly line is gone and all is well in malware land. Now, what we are now the agenda is to actually make this function pointer point to a place where this function is defined, right? So that's exactly what we're going to do. As we saw in the debugger, this function resides in the ntdll.dll. And as we see from PE Studio and the general conception, because all of the functions further ahead are going to be using ntdll.dll, that it will be loaded by itself. So what we're going to do is create a new variable which will point to ntdll. Right? So this will create a new variable called ntdll, and that will point to the module which will be loaded into the memory. Now, what we want to do is define a new function, right, using this particular function pointer. So what I am going to do is create a new variable called fox open, right, and it's going to be of the type function pointer pointing to a function of type NT-open process. Okay, now let me explain what this particular line of code does. What it's going to do is it's going to get the procedure address NT-open process from the module NTDLL, and I am identifying NTDLL using the handle that we have just created. Now this will get the procedure address, typecast it into NT-open process explicitly, and then assign that value to fox open, right? And now this fox open is ready to be called. And as you can see, now even Visual Studio Code is telling us that now we can actually use this as NT-open process. Now let's head back to NT-doc and see exactly how this is supposed to be called, right? So the parameters over here, the first one is process handle, which is going to be a pointer to the variable that receives a handle to the process. So that in our previous code was hprocess, and we need a pointer to that. So we'll put hprocess over here. The next is access mask. So for us, this I'll put it as process all access. You can obviously minimize it to exactly how much permissions and privileges you need, but let's keep it process all access for demonstration purposes. Next is object attributes. All right, so when we open the object attributes NT-doc, we see that a lot of things, a lot of parameters present in this can be null. However, the length is something that they have explicitly told us to put as size of whatever object it is, right? So let's actually go and do that and create a new variable of type object attributes. Let's call it and the rest of them can be null. One more thing that we have to do is create another variable of type client ID. Now this says it's optional, but if you go and take a look at what this holds, then this actually holds the process ID to which you need the handle to. So this for us is not optional, this is exactly what we need, and this is exactly what we want. So let's create client ID. Initialize it as null, and give it this value, give the process value, the value of the PID that has been given to the project or the binary as a command line argument. Now once that's done, let's move ahead to calling this function. Now here we need a pointer to the object attributes object. So it's going to be object attribute, and then it's the P client ID. So again, client ID, and this should work. This should functionally be able to replace this particular few lines of code. So this is essentially replacing this, and the further error handling is being done on H process, so we don't really have an issue with that. We can definitely let that happen, and everything in front of it, ahead of it, should happen automatically because we have successfully retrieved the value of H process just from this, right? So let's go ahead and compile it. Right? So we do have some warnings, but no errors. So that means this has successfully been compiled, and we can test it out to see if it is even working. Five one three two. Okay, and we see this particular calc.exe popping up here, and this is completely functional. And the other PowerShell window this time has been killed by itself. So remote process injection has successfully been done. Now let's take a look at how PE Studio actually, looks at transition.exe. And while that happens, we can load it up in the debugger. Have a new PowerShell session. Actually, let's put it over here. And we can also boot up process hacker just to see what's exactly happening. What we are interested in are the handles of the process 17716. 17716. Right. So these are the current handles on the process 17716, and we are going to change the command line to reflect 17716 over here. Reload the binary, and then see if anything changes after we run this particular code. So I'll go through with this over here. Yes, so the breakpoint is on main, right? So here is the main. Now what you will notice, what I'll display first is that now there is get module handle and get procedure address here instead of the get or rather the open process. And you can't see open process here. The next call you can see is to get last error, which is the part of our error handling procedure, which you can see over here. So get last error and get proc address. There is no other Win32 API call recorded as far as you can tell from the assembly over here, right? So let's actually see how this turns out for us. Let's get ahead till get module handle. So this right now will get a handle to ntdll.dll, this call racks. And now the procedure nt open process will be fetched and it will typecasted, or rather the new variable will be assigned to it. Now we have this long code over here, which is essentially us making those structures, those object attributes and CID structures. And then we have another call over here, which right now, as you can see, is ntdll.zw open process, right? Why is it zw.open process? I'll get to that. Now, once we step into this, I want you to see that we're going from transition.exe, right? We're in the memory space of transition.exe. As soon as we step into it, we are directly into the memory space of ntdll.dll, and we have skipped kernel32.dll and kernel-based.dll altogether. So what we can see is that now once we get that syscall done and return, we are right back in transition.exe and the flow goes on, right? Now if we take a look at the handles, we see that there is this new handle over here from transition.exe, same code that I am running right now, and the value is oxa4, right? Now let's go take a look at what this one is going to say. We go a few instructions ahead, and after our error handling, we are able to see that the program says the same, right? So essentially we have received the handle and the rest of the code exists as it does. And moving to P Studio, what we see in the import section is there are still flags there, but there is not one for open process because open process has been removed completely. And since we cannot interact directly with NT open process, there is no point of having, or there is no way that NT open process would show up here. However, it is to be noted that we can still see it getting flagged in the strings, the NT open process, because we did in fact put this as a string over here. We can obfuscate it or write a code in such a way that this gets dynamically put together when the binary is running to avoid this. But that is just something that you would do to enhance your malware. However, we have successfully removed open process from the import address table. Now, as an exercise, I have also replaced each and every one of those API calls from the code, and this is basically just the same shellcode injection by using the native API for each and everything. So here I populate all the native API together, right? And then one by one, I call them and do error handling based on the output I get. Now, one thing to note is that all of these functions, they have a return type of NT status, which basically tells you if the native API was successful or if there was an error. So you can use the return value as as a part of your error handling as well, as you can see here, right? And if you want to take a look at how the execution looks for the native API, you can do the same. So here is the native API. Let's put it in PE Studio. And while that happens, let's take a look at the main, right? So here is the main. And as you can see, what we can see is that there's get last error over here, get module handle, and then there is a series of get proc address over here. But there is no virtual alloc, no write process memory, and the code just ends like that, right? So these functions are not directly called. Now, getting to what the difference between ZW open process and NT open process was, for that, let's head towards the first API call that we will do here, which is the NT open process. I think it would be somewhere around here. Let's put a breakpoint over here, right? So NT API have been populated, and this particular call will be to ZW open process and not NT open process, which we were targeting, right? So let's see what the discrepancy is. As soon as you go here, what you can see in the symbol is ntdll.dll getting highlighted. You can click on it and see the different functions it has in its memory space. And with this, you can also spot what functions memory space we are currently in. So currently we are in ZW open processes memory space. And if you try to spot NT open process, it should be here somewhere only. There. Yeah, so the NT open process also is green. And if you take a look at the address, right, if you click a screenshot, make a note of this, and then come down here where ZW open process is and compare the two values, you'll find that they are exactly the same. So from the user perspective, both of these functions are exactly the same and you can use either one, right? If you go to ntdoc and you type ZW open process, you will see it here, but it will lead you to a URL meant for NT open process only. So that is where that particular discrepancy comes in. Looking at the PE Studio, we can see that there are still flags here. Some flags which we were not able to remove, but which we were not using for virtual protect and virtual query. Rest, all of them have been removed, but you can still naturally see all the strings, right? So we have successfully used native API to conduct a shellcode injection into a remote process. Now let's answer some of the questions that we have received. Right. So the first question is native API or NT API the same as using syscalls directly? Okay, so as you saw that Win32 API was essentially a wrapper built around native API, the same way you can say that the native API is a wrapper built around syscall. You can definitely call, perform a syscall directly from transition.exe or like the malware.exe. However, that in our case, what we were doing in today's video was being done through the native API. You can go down one level of abstraction lower as well. You can definitely do that. Can EDRs still detect malware that uses NT API? So native API has recently gotten very popular for writing malware. So earlier, the same hooks which were placed on Win32 API have been the EDRs have started putting those hooks on the native API. So therefore, the EDRs can definitely tell if you're using the native API directly. The way to beat that is to use syscalls either directly or indirectly based on whatever environment you're in. Indirect syscalls are the better way to go. Do leave a comment down below if you want me to make a video on direct and indirect syscalls. I'll do that as well. Is native API something beginners should start learning right away? So you can put off learning native API as long as you're not getting comfortable with Win32 API. Once you get comfortable with using Win32 API to write malware, right? Once you get comfortable with using the API used to interact with Windows in general and the structures and the debugging that is required, once you're through that, then you can definitely look at understanding how native API works and how you have to use the reverse engineered documentation that's there to write some malware. How does NT create thread X differ from create remote thread and why does it matter? So as we saw, NT open process had a wrapper built around it, which was the Win32 API for open process. Similarly, the NT create thread X is the native API call, which actually performs the syscall required to do the function, and it has a wrapper built around it, that is the Win32 API call for create remote thread, right? So it's exactly the same, and if you want to replace each and every one of those Win32 API calls, you follow the exact same procedure. You don't have to go into the debugger and see exactly what is happening, but you would have to go there once to see what native API is actually below the hood of every Win32 API call, right? Let's also take a look at the comment section. Okay, so Shashi says, nice haircut. Thank you very much. And which programming language should I pick to start with Evasion? Now, I feel the most comfortable one to start with Evasion is C, because these libraries that you see over here at the very top, windows.h, stdio.h. Okay, so stdio.h is not that big of a deal, but this windows.h is something you cannot really directly import in each and every one of programming languages. You usually have to use platform invoke to interact with the Windows 32 API if you're not using C or C++. So if you want to start with malware development in general, or you want to move from malware development to evasion, I think the easiest way to understand how that works or how to actually get the job done is by using C. You can obviously port this code over to different languages, but I think the ones that you should really focus on while starting out are C and C++. So that's it for the Wednesday live. Thank you everyone for joining, and do leave comments for different topics that you would want me or other consultants to pick up on for the rest of the Wednesday live sessions. Thank you and bye bye.